This video we are going to solve a problem in design of welding, particularly eccentric loading. When the load acting plane is perpendicular to the welding plane, how we are going to solve the problem? Okay, let me start the problem now. The bracket arrangement is shown in figure. The protruding portion of this bracket consists of the T cross section with the dimension indicated, and the welder is supported by the plate. So actually T cross section the plate is welded with the vertical plate, and they have mentioned that in the welding these portions are welded except the smaller portions. So the portions are welded is mentioned here, 1. So similarly 1, then 2, then 3. These portions are welded and the entire thing is given in the diagram. The load to be supported is 40 kilonewton. Find the necessary weld size for the connection between the protruding portion and the support plate. The maximum shear stress in the weld should not exceed to 100 Newton mm square. So at the end of the plate, the load is applied, which is 40 kilonewton, and the maximum allowable shear stress is 100 Newton per mm square. We need to find the size of the weld. So here, for the given data, the load value which is applied at the end of the extruded plate, that is 40 kilonewton, so 40 into 10 power 3 Newton. And the eccentricity from the welded portion to the load acting point, the eccentricity value is mentioned in the diagram, that is 300 mm. So eccentricity 300 mm, load value 40 kilonewton. And the welded portion is mentioned in such a way that it is like a T-shaped one. So here the top portion of the T and the bottom portion and the vertical portion. So totally 100 mm, then this one is 40 mm and 40 mm, again 100 mm, 100 mm. So these portions are welded, they are mentioned, and the maximum allowable stress is 100 Newton per mm square. So how we are going to solve the problem? So here the condition is the load acting plane and the supporting plane, that welding plane, are perpendicular to each other. Here this is the welding plane, and here this one is a load acting plane. So load acting plane and welding plane are perpendicular to each other. So there will be two different stresses induced on the welding. So there are two cases in eccentric loading when load acting plane and the welding plane are parallel or same. And another case is the welding plane and the load acting plane are perpendicular. So there are two cases. So already the case number 1 is solved and uploaded in our playlist, and this is case number 2 for eccentric loading when the welded plane and load acting plane are perpendicular to each other. Okay, let me solve the problem here. So at the particular case, and due to the eccentric loading, there are two different stresses will be acting. One is due to the direct loading, direct shear will be applied on the weld. That is direct shear load by area we have to calculate, and after that, due to the eccentrical of loading, there will be bending stress induced on the weld. So we have to calculate the direct shear stress and also the bending stress. And after that, using the maximum shear stress formula, we have to combine the bending stress and shear stress, and we need to calculate the equivalent shear stress, that is maximum shear stress. And from that, we can calculate the unknown size of the weld. So in direct shear, the formula will be load by area. The load is given in the problem, and area is nothing but length of the weld and the throat thickness. And in the bending stress formula, sigma B is equal to MB by Z. MB is nothing but bending moment, load into eccentricity, and this is just nothing but section modulus that can be taken from design data book, PSG design data book, page number 11.6 for the particular cross-section weld. Okay. And after calculating tau and sigma value, we have to combine the stresses by using the maximum shear stress formula that can be taken from design data book, page number 7.2. In 7.2, principal stresses formula will be there. From there, we can take the maximum shear stress formula. Fine. Let me solve the problem. So first thing is, we need to calculate the direct shear stress. The formula will be load by area. So load is already directly given in the problem. The load value P is equal to 40 kilonewton, that is 40 into 10 power 3 Newton. And the next thing is we have to calculate the area of the weld. Area of the weld is nothing but length into throat thickness. So here for the length of weld is 100 mm, then 40, then again 40, then 100, then 100. We have to calculate the total length of weld. So 100 mm, and here 100 minus 20, that is 80 mm. So 100 plus 80 plus 2 hundreds. So 2 into 100. So these are the total length of the weld. So one by one we can write and we can calculate the area of the weld. So length is equal to, first thing is the 100 mm plus this side 40 and this one is 40. So total 80 mm and plus this one 100 and another 100. So 2 into 100 mm. So this is the total length of weld into throat thickness. T is equal to 0.707 height. Height is nothing but your welding size. So here by calculating the area of the weld, total length into throat thickness, that is equal to 268.66 into welding size. And the direct shear stress, tau is equal to load value 40 into 10 power 3 and area value 268.66 height. So then we can calculate that the final value will be 148.8 divided by height. The unit of shear stress is Newton per millimeter square. That's it. So we can leave the stress in terms of height. And next thing is we have to calculate the bending stress. So in bending stress, MB value, MB is equal to load into eccentricity. Load is 40 kilonewton, so 40 into 10 power 3. And eccentricity value 300 mm. That is taken from the diagram. So we can see here the eccentricity value from the welding to the load acting point. The distance is 300 mm. So we have taken the eccentricity 300. And by calculating the bending moment, 40 into 10 power 3 into 300, that is 12 into 10 power 6. Unit of bending moment, Newton millimeter. That's it. And the section modulus Z value can be taken from the design data book, page number 11.6. So here various diagram will be given. And based on our given diagram, that is T section. So here the T section, we can take the Z formula. The mentioned Z formula is 4BD plus D square divided by 3. So here in the data book, they have considered welding as a line. So the formula is directly given, and actually in the problem we have to consider the throat thickness also. So we have to multiply the formula taken from the data book into T. So here the welding is considered as a line, but we have to consider the thickness. So we have to multiply with the taken formula. So actually here in the formula from the data book will not have any T value. Actually, in the problem, we have to multiply the T with the formula. Fine. So by calculating Z value from the data book, Z is equal to, and in the diagram itself, they have mentioned that B is the width of T and D is the total height of T. So here 100 mm, that is B value, and D is 100 plus 20, 120 mm. So by substituting B value and D value in Z formula, 4 into B value 100, and D value 120 plus D square 120 square and divided by 3 into throat thickness T, that is 0.707 into height value. So by calculating the given values for Z, the value will be 14705.6 into height. So after that we can calculate the sigma B bending stress value. Sigma B is equal to MB by Z. MB value 12 into 10 power 6 Newton per mm and Z value 14705.6 height. Simplifying that, the final value of bending stress, that is 816 by height in the unit of Newton per mm square. That's it. Now we have calculated the direct shear value and the bending stress value. And after calculating the shear stress and bending stress, we have to combine the stress value using the equivalent shear stress formula, that is maximum shear stress formula. That formula can be taken from design data book page number 7.2. So from the formula, sigma x and sigma y, the stress induced in x direction, stress induced in y direction. So here only one sigma is there. So in perpendicular direction, there will be no stress. So sigma x is equal to sigma b and sigma y is equal to 0. We need not to take any stress on y direction. So there is only one sigma that can be considered as sigma x, unidirectional stress. And by substituting here, tau max is equal to 1 by 2 root of, instead of sigma x, that sigma value 816 divided by h the whole square plus 4 into tau value that already calculated 148.8 divided by h the whole square. And by simplifying that, the value will be 434.3 divided by h. So that is the maximum stress value. In the problem, the maximum stress value is already given, which should not be exceeding 100 Newton per mm square. So by equating the tau max value to 100 Newton per mm square, we can calculate the height, that is 4.34 mm. So this is your size of weld. By round of the value 4.34, that is approximately equal to 5 mm. We have to choose the next higher value. So 5 mm is the welding size for the given condition. Thank you.